Okay, so in this video, I want to talk about the double descent curve, and that is something you can see in the random features model. So I'm going to describe this really nice graph from this recent paper that I really liked, and this is exactly the setup we've been looking in. So let me tell you exactly what they did here. So what we're looking at is we're fixing some distribution mu of data. So we have some distribution mu of data points, which give you x and y. And imagine that you see some number of training examples. So the number of training examples, we call that nx. nx, you see some number of training examples which are drawn IID from mu. That's the number of training examples you see. We have the number of parameters in our model. That was we said you can do more and more, and we're going to do the random features regression model, so we can make the number of parameters as large or as small as we want. And there's one last thing which is in the problem, which is the input dimension. That's the size of the inputs. And those are the three numbers in the problem. And what this paper did is they looked at a limit where all three numbers are going to infinity, but their ratio is staying constant. So they gave these things names. So they said, let's call phi 1, I believe was, so phi 2 is the number of parameters divided by the dimension, and phi 1 is the number of examples divided by the dimension, if I'm not mistaken. And what they looked at is they looked at the generalization error and how it depends in this limit on phi 1 and phi 2. And what is the generalization error? So the generalization error is how your model does on something from the distribution mu that was not in your training set. So it's the expected value under mu of your model at time infinity after training minus the ground truth, say squared. So using the things we've done, you can get an exact formula for what will happen after training, and you can compare that to an unseen point from the distribution and see how it depends on all these things. And what you see is this double descent curve. So what's plotted here is the test error. That's the error we were describing, how you do on an unseen point, the expected value of f minus y squared. And what's plotted on the x-axis is the ratio of the number of parameters in your model, the number of parameters, and par, divided by the number of examples. So that's plotted on the x-axis. And what you can see is something interesting happens at 1. So when on the x-axis, when you're equal to 1, that's when the number of training examples is exactly equal to the number of parameters. So classical statistics says that if the number of training examples is equal to the number of parameters, or if the number of parameters, as you increase the number of parameters, as you get close to this situation where the number of parameters is equal to the number of training examples, you might start overfitting. And that's exactly what you see on the first half of both of these curves. So first, your training test error is going down, and then it starts to go up and up and up again as you get close to this point where the number of parameters is exactly equal to the number of examples. And that's because you're sort of like perfectly fitting the data. So this is classical statistics telling you, hey man, you might be overfitting when the number of parameters equals the number of examples. And on the right plot, it's the same situation, but there's regularization, and that makes it a little bit less of a problem, but you still see the same kind of shape of first you're doing good for a while, and then you start doing worse as you add more parameters back in. So that's classical statistics, is the blue curve. You go down for a while, that's good, and then you go up, that's overfitting, that's bad. But what's interesting is when you're very over-parameterized, the error starts to go down again. So that's the second half of the curve, and that's why it's called a double descent curve, because the error starts to go down again. And what these people have shown is that in this very simple model, through some very complicated calculations, that the training error starts to go back down again as you get more and more over-parameterized. So the more features you add in, even though they're random features, you can figure out exactly what happens, and you have this phenomenon of the double descent curve, where classical statistics still works and says sort of you get more error when the number of parameters is equal to the number of examples, but past that, things start to get even better. So it's a double descent curve, and we have this whole new field that sort of classical statistics didn't know about on this side of the double descent curve.